Alright, how you guys doing today? Thumbs up, nice to see. I'll check actually before I say something incorrect. All right, good day. It's Wednesday the 17th, and our plan for this week is to continue and conclude Chapter 8. Chapter 8 assignments are already up, and by Monday we will have covered everything, and I encourage you to bring homework questions to class with you on Monday, the 22nd. However, I'm going to make the homework due on the 29th. My goal is not to give you something to do over Thanksgiving. I just figured some of you might like the extra time to work on it. So you do not need to work on it on Thanksgiving itself. If you wrap it up before that, fantastic. I just wanted to err on the side of caution, give some people more time if they wanted it. Next Monday we'll also start talking. Make sure to go over plenty of review information for the upcoming test 2 and exam. Right now we're going to focus on concluding Chapter 8. And so today we'll continue talking about torque and other rotational principles. Before we get started with that, do you have any and all questions? Okay. So last time we introduced and utilized torque to some extent. Torque is the angular equivalent of force. We looked at the formula, we calculated a few things, and I want to begin today by pointing out, as I've mentioned with most of the rotational concepts up till now, all of the logic for the linear version of the concept still applies to the angular concept. So, if we look at static systems, systems in equilibrium, where objects are either remaining in place or are traveling at constant velocity, if all the forces, linear forces, acting on a mass add up to 0, the object will remain as it is. Similarly, if all the torques on an object add up to 0, that object will be in rotational equilibrium. It will continue to rotate as it currently is. That could be not rotating at all. That could be rotating at constant velocity. Bless you. Bless you again. So it is possible to have more than one torque acting on something. Say, for example, I'm grabbing one piece of this wheel and trying to make it spin in one direction. Someone else could grab another part of the wheel and oppose me, generating torque to oppose the torque that I'm creating. If our two torques equal each other, they should cancel out and the wheel shouldn't spin. Similar systems happen in your car. There's lots of moving parts and parts that want to be moving but aren't. And if the torques on a specific piece all combine to form 0, then it will just either not rotate or rotate at constant velocity. We have used this principle in lab, and we're going to look at another example today that will also utilize this principle. And to any possible bio majors who've been wondering this entire semester why you need to know any of this, well, the human body does run on physics principles, so let's specifically examine how torque works in a specific case involving your bones and muscles. Here we have someone engaging in a less than optimal way of holding a shot put. They're just going to hold it straight out like this. They're just holding the one heavy object. You can call it a bowling ball for simplicity if you want to. But it's a heavy object that is being held straight out horizontally from the elbow. The arm is just tucked down at the side like this. Now, to any persons who have engaged in athletic training or possibly just moving heavy things, say on moving day, is this the best way to hold something heavy? No. If you were just to think, oh, I have to pick something heavy up now, the best option is to have someone help you, because that reduces the strain on your body. But if you have to carry it yourself, typically you tend to lean back so that the object is better supported by more of your body than just this one part of your arm. We're going to look at why, mathematically, this is a poor way to do things. There are, very specifically, 2 different torques on this arm right now. The first torque is the one caused by the shot put itself. If hypothetically we just, like in your high school bio classroom where there might have been a plastic skeleton in the corner hanging up, if you were to just hold that skeleton's arm out like this and put a shot put right there, then what would immediately happen? The arm would rotate out from under it and the shot put would fall. That is because the force of gravity pulling down on the shot put acts at some radius away from the elbow joint, and that will generate a torque that will make the arm begin spinning out from under the shot put, at which point it will just fall straight down. So that does exert very specifically a torque on your forearm, which this diagram calls the ulna. Is that incorrect? I don't know. I don't know the bones in my own body, frankly. So that is one of the 2 torques that are present that must add up to 0 to hold this object in place. The other torque is created by your bicep. Well, at least in this case, it's created by your bicep. I know in real life there's other muscles that are doing things at the same time, but in this worst case scenario where the bicep is the only muscle holding it up, I don't know the names of the other ones. We're just going to examine specifically how the bicep stops your arm from falling straight down. Now, in terms of physics, I find this neat. This might not be a novel concept to some of you, but your muscles do not anchor specifically at the joint of rotation. If this muscle rooted right here, why would you not be able to move your arm? Notice, if the muscle roots right here, some distance away from the elbow, it's now at a radius from the pivot of rotation, which means now at this point, the force upwards from the bicep is perpendicular to the axis of the forearm, which means at that distance, it can generate torque. And torque is specifically how you move at least your forearm up and down, because it is rotating about the central axis of your elbow. If the muscle's connected here, the radius would equal 0, in which case, no matter how hard you strained your bicep, there'd be no torque, your forearm wouldn't rotate. So it very specifically roots some distance away, very much on purpose. I find that very neat. And that is the second torque present. There's 2 torques here. They have to cancel out and add up to 0 in order for you to be able to hold your arm in place with that weight right there. Any questions about the physical setup so far? Okay. I want to pass this off to you guys for real quick. We know that there are 2 torques present. They have to add up to 0. I'll also rewrite the torque formula, just in case. And my question to you guys is, I'll give you a couple minutes to work on your own or with your classmates. What must the force that the bicep is exerting be for this situation to be balanced to hold your arm in place. What is the force that the bicep must exert to generate the needed torque to hold your arm still? Give you guys a couple minutes. How are we feeling so far? So is allowed. So we're going to check our answers. Anyone have a number to present yet? Say again?
583.
583. Does anyone's math either agree or disagree with this assessment? No votes here or nay? So this is the correct answer for the perpendicular force that the bicep would need to exert to hold your arm in place. Let's look at how to arrive at that answer and then what we need to do further. So, we know that there's two torques on this arm that need to add up to 0. So sum of the torques equals 0. Let's add the two torques together. We've got torque from the, can't write, shot put, and additionally torque from the bicep. Those are the two things that are acting on the arm to hold it in place. And those will be equal, those must add up together to 0. The torque exerted by the shot put will be equal to its radius from the elbow times its own weight. So that radius is 0.35 times the force of 50. And the bicep, its torque is based on its radius from the elbow of 0.03 meters, and the perpendicular force it's exerting is specifically what we are after. I'm going to go ahead and note one minor tweak to just this line of things. The bicep force points upwards, and the weight of the shot put points downwards. Those two torques do oppose each other. The shot put wants the arm to rotate clockwise. The bicep wants the arm to rotate counterclockwise. So the forces are in two different directions. That's still important because they are opposing each other. So best practice is to make this one negative to reflect that fact. If we make that one negative, we will ultimately get a positive answer, which is what we would expect if the bicep is specifically pointing upwards for the most part. If you didn't do this, you might get a negative answer for force, which just says it's in the opposite direction as the shot put, which makes sense. From here, if you calculate perpendicular force, this is the number you should get. You guys agree? At least a few nods. All right, very good. So this is the perpendicular force the bicep is exerting on the ulna. First thing to note, this is a lot more than what the shot put weighs. This is one reason why holding things like this is not great. It is not only inefficient, it could possibly hurt you, especially if you end up dropping it on your foot. Because of the way that the torques are applied, the bicep does have to exert more force than what this object actually weighs, which is one reason why weightlifting is a very complicated endeavor and why the body is designed in a very meticulous way to make all of this work in a very harmonious fashion. I also think in general there's probably more muscles at play here than just the bicep. So hopefully all that force is not located just on the bicep itself. I just don't know what muscles those are or where in the arm they go. This is just the math we're presented with right now. I'm comforted at least knowing there's other muscles helping the bicep, so not all of this load is specifically in just this part of my arm. So in the real world, this number would probably be reduced. This is a worst case scenario, I think. But still, it's kind of eye-opening. There is one other detail though. This number is not the entire force within the bicep. This is the perpendicular portion of the biceps force. Because upwards, vertical, is perpendicular from the length of the ulna. But notice that, and this is true in your own arm, the bicep isn't completely vertical. It's shunted somewhat at an angle because it connects away from the elbow down here, but it connects closer to the actual joint at the top of the humerus. I'm sorry if I'm butchering biological anatomy here. I'm just going on what the picture says. So the actual bicep points this way, and this is, I'm moving it slightly from the actual picture so that things aren't quite as on top of each other. This would also end up being 8 degrees. And so this represents the triangle formed from the bicep itself and the vertical force that we just found. Technically, the bicep would have to work a little bit harder because it's the hypotenuse of this triangle. Again, in real life, there's other muscles to help compensate for this. But one last step, I'll leave you guys real quick. What is the actual final bicep force if this is the vertical leg of this triangle? $588. Does anyone agree or disagree? Give some thumbs up. All right. Let me check something real quick. 583 points. Because in my calculator, I had the full number left over from the earlier calculation. I'm going to use just cutting it off at the 3 real quick. All right, I'm getting closer to, and a degree of rounding like this is not a problem. I'm getting closer to 589 approximately. If you're at 588, that is okay. The way that we get to this particular number is, we want the hypotenuse, we know the adjacent leg of 8 degrees, so I would recommend cosine of 8 equals bicep force, whoops, I did that backwards, equals the vertical leg divided by the bicep force. So we would bring bicep over here, divide by cosine of 8 degrees, and we would get a slightly increased number. It's not a big adjustment, but it is worth noting that this is the physical reality. And if the angle was any steeper, or rather if that numerical angle number was any bigger, the discrepancy would become even wider. So, any questions? How do we feel about this one? Okay. Please let me know any questions you have at absolutely any time. I'm going to give us a quick pause real quick while I get ready for the next principle that I want to show you, because I'm about to talk about one of my least favorite things in this chapter. And we're going to spend the rest of the day introducing it, and we'll spend Friday actually utilizing it. So, pause real quick. Need water, restroom, etc. Now's a good time. Does anyone object to me erasing this? Okay. There is a homework question very much like this one. It also involves a bicep. So the math that we did here will be very relevant to that. questions, needs, concerns, etc.? Okay. I immediately lost my train of thought. Probably not a good sign. So, torque is the angular counterpart of force. We've already said several times that all of the logic in all of the formulas from the linear world still work in the angular world. You just literally want to replace the linear concept with its angular counterpart, and all the logic, all the formulas should still work. That's why that on the formula sheet, the formulas for linear versus angular are listed in columns diametrically opposed to one another that show how similar they are and shows the translation equations between them. They're very similar, all the logic still works. We also have formulas that, in the middle column there, show the translation between linear and rotational. I want to ask you a quick hypothetical question. Is this formula for torque the rotational counterpart to this classic definition formula of force? A couple people shaking their heads in a few different directions, and a few inquisitive glances. That is okay. It's a weird question to ask. This formula for torque is not the rotational counterpart to this formula for force. All of the rotational linear counterparts so far have been the same formula, just with the concepts swapped. So this is linear Fantastic Four equation number 3. The angular Fantastic Four equation number 3 is all the same concepts, just with the rotational variables instead. Everything's still in the same place. For these formulas, force and tension are opposite counterparts, but mass and radius are not counterparts, and linear acceleration and linear force aren't counterparts. So this is not the angular counterpart to this formula. This is actually the translation equation that takes us from linear to angular. This formula is more like the ones in that central column that allow us to take a linear concept and turn it into its angular counterpart. It has its own unique quirks, but it's of the same variety. It's a translation, it's not a unique rotational only formula. So the rotational only version must exist. Let us now determine it by just taking the original Newton's second law and ripping out the linear stuff and replacing it with angular stuff. So we've got linear world, translational zone, angular world. We're just going to rewrite the formula with angular variables instead. What's the angular counterpart to linear force? Starting from left to right. Angular counterpart of linear force is torque. So the beginning of the rotational only formula should start with torque equals. So we're taking force out, we're just going to replace it with its angular version. I'm going to skip mass. I'll explain why later. The last variable is linear acceleration, and that needs to be replaced with its angular counterpart, which is angular acceleration. This makes sense. Linear force on a mass makes it accelerate. Angular tension on some object with mass causes it to rotate. Torque creates angular acceleration. I've said this several times, so this makes sense so far. Mass is the tricky part. No wrong answer here. Ignore the magenta screen color. Do you expect mass to have an angular counterpart? Some people are saying no, and frankly, when I was a student, I wouldn't have thought it did either, because it's not a vector. Whether or not an object is moving in a straight line or rotating shouldn't really matter, because the mass isn't a vector, right? Time's not a vector, and it doesn't have an angular counterpart. But tragically and frustratingly, mass does have an angular counterpart. It's not the same thing in both versions of the formula. And I will explain how we know this in a minute, but to go ahead and complete the formula, torque equals moment of inertia times angular acceleration. The angular counterpart to mass is called moment of inertia. As we've said, linear force on a mass causes it to linearly accelerate, therefore angular torque on some object with mass that can rotate will then angularly accelerate. So these two formulas are counterparts, and whereas if all the forces and torques added to zero is a static system, if the forces and torques aren't zero, that's a dynamic system where things are moving, things are spinning, usually. Planes are a pretty good atypical example of that because they tend to literally turn by doing barrel rolls and things to that effect. So they have to rotate in order to be able to turn. So a plane is a dynamic system, both linearly and angularly, just as a sample. Now, I'm a professional physicist, and I don't like moment of inertia. It is probably my least favorite thing to have to go through in this section of the class, because I'm upset that it needs to exist. I'm upset that we can't just use normal mass. Tragically though, the math doesn't work if you just plug mass in instead of the moment of inertia. This is because normal linear mass measures an object's innate tendency to want to move exclusively in a straight line. Objects with more mass are harder to stop once they're moving in a straight line. That concept refers to either the object's inertia, possibly its momentum if you're calculating that. Linear mass, regular mass, only refers to propensity to move in straight lines. All objects have different propensity to rotate depending on how you rotate them. Take this wheel, for example. If I was to ask you to spin this wheel, you would probably do this, because this is the axis about which a wheel most easily rotates, which is why we use wheels like this. However, there are other less efficient ways to spin a wheel. For example, I could do this. Is this a good idea? No. It is not spinning very easily, and this hurts my hands, but you could spin it that way, and this object has a different propensity for spinning about that axis than spinning how it normally does. It's literally easier to do this because the object wants to spin this way. It's harder to make it spin the other way, even though the wheel has the same mass and is the same shape. How it spins affects how easy it is to spin it. Another example, I am going to rotate my calculator lid, specifically by throwing it into the air. I'm going to spin it 3 different ways to show you its propensity for spinning in each of those axes. For simplicity's sake, let's just assume that this is a complete rectangle instead of a weird partial shape. A complete rectangle, it has a mass, it has a length, width, depth, all that good stuff. And I'm going to spin it about 3 different axes. First, I'm going to throw it in the air like this, through its longest side. Then I'm going to throw it in the air like this, rotating about one of its longer sides. And lastly, I'm going to do it like this. And we're going to watch it to see what effect changing it like this has. So first, through its longest axis. I'm not very good at this. In your professional opinions, was it rotating fast or slow? Pretty fast. Hold on to that rough speed approximation in your minds. I'm going to throw it in the other 2 orientations, trying to use the same amount of force from my hand each time. Next, we're going to go like this. Bless you. In your expert opinions, was it rotating faster or slower? Slower. It has the same mass, it's the same object, it is the same shape, and yet the axis through which it rotated affected the rate at which it rotated. I exert the same force on it, and yet it ends up accelerating to different final velocities, angular velocities, because it has a different moment of inertia through each axis. The last and most infuriating one, I'm now going to throw it like this. I want you to pay close attention to it. You can replicate this yourself with your phone if you want. Notice anything weird about that one? Some of you seem to catch on to it. It does a backflip in midair. Again, if you've ever just casually been tossing your phone around or a similarly shaped rectangle, you've probably noticed it turn once or twice in midair. It literally is doing a backflip. It's not a trick of the light, it literally happens. In fact, if you throw your phone enough times, I guarantee eventually it will land in a different orientation to how you threw it, either backwards or maybe upside down. For a reason I can't fully explain, whenever rectangles rotate through this axis, the torques acting on it just cause it to do that backflip if it's free to do so. It's a weird quirk. I can't fully explain it, but its moment of inertia and the torques involved command it to do so, which is further proof that every single different axis this thing spins through has a different moment of inertia, despite the fact it's the same object with the same orientation and the same mass. It infuriates me to no end, but it means that we do have to calculate different moments of inertia for every object, every different way it spins. Now, because I dislike this fact, I do try to make these parts of questions as simple as possible. There exists on the class formula sheet a table of various moment of inertia formulas, showing again, these are all sometimes similar objects, sometimes it's the same object orbiting in different ways, that show an object's moment of inertia always depends on its mass and its shape, and then its size as well. All of these formulas involve the object's mass being multiplied by some radius or length squared. And yet, they're all different depending on the exact mass's construction and what axis the mass ends up rotating through. The first 4 entries here, you will never have to memorize any of these. These are on your formula sheet. In fact, the one homework question where there's one homework question that's entirely about using these concepts, and that question has this table in that question. The first 4 objects, even if they all had the same mass and the same radius, they would all have different moments of inertia. They'd have different propensities for spinning. Such that if you were to line up a hoop, a can, a cylinder, a hollow sphere, and a solid sphere, that all were the same radius and the same mass, if you lined them up on a hill and let them roll, they would reach the bottom at different times, because it takes different amounts of effort to make them spin because they have different moments of inertia due to their shapes. Then, these 2 cases down here, both refer to the same object. You can take a long, this is a tube, it would work with something blocky or triangular as well. You can take some long, let's just call it a pipe for right now. It has the same mass, the same length, but its moment of inertia will change based on whether or not it spins about its very center, so kind of like this, or if it spins about one of its ends. It'll have a different moment of inertia and a different propensity for rotating each of those different ways. Here there's a constant of 1/12 out front. Here there's a constant of 1/3 out front. You will never need to memorize any of these. I will make sure that either the shapes in questions will match the ones on this table perfectly, or the question will give you all the variables to find moment of inertia some other way. Or I'll just tell you the moment of inertia. This is just kind of a necessary evil when it comes to looking at things rotating, because mass shows up in most of our formulas. Therefore, moment of inertia shows up in the angular forms of all of those formulas. I don't like it. And yet, I can't get rid of it. So I'm going to try to make the examples that use it as straightforward as possible. The variable for moment of inertia is a capital I, which at least matches the inertia part of the name. The unit for moment of inertia is kilograms times meters squared. The unit for normal mass is just kilograms. The unit for moment of inertia is kilograms times meters squared. This unit comes from the fact that every single one of every moment of inertia formula, there's even beyond just these 6, all has a mass term in it multiplied by either some radius or some total length squared. So every formula has kilograms and then multiplied by meters squared in it. So they all come out with the same unit. It's primarily just a question of what fraction is on the front of the specific equation in question. Now, we're at the end of lecture time, so I don't want to start a big example at this point. So I'm going to let this sink in. We'll do a quick review of it on Friday as we introduce some other concepts that utilize some of the formulas that have this moment of inertia in them, so we can show how it functions in the concept of mass. Just let it sink in for now. Keep working on the homework, and let me know if you have any questions. If you don't have any right now,